Hello, everybody. I'm Jordi Baylina. I'm the technical lead at Polygon zkEVM. For you that you don't know, Polygon zkEVM is mainly a layer 2 rollup. It's compatible, full equivalent with Ethereum. So you can have a Solidity, you deploy a smart contract, you use just hard hat, you use exactly the same tooling. Instead of deploying to Ethereum or Polygon, you can deploy it to the zkEVM, and everything should work exactly the same. The only thing is it should be cheaper and faster throughput. Okay? Before getting deep a little bit to the content that I want to talk about, just want to give you a bit of the roadmap of what we are doing right now in the Polygon zkEVM team. Mainly we're working in different fronts here. We have, for example, the forced transactions. This is for censorship resistance. We want to enable that as soon as possible. We're working really hard on that. Very soon you will hear some news from some bug bounties. For this is, I mean, from the security perspective, it's a little bit risky because this opens a lot of vector attacks, and we want to be very sure on that. But we are working hard on that direction. There is also other types of work. A lot of them related to optimizations on the prover that we will talk later, but also optimizations in the client side and so on. Then there is the biggest bottleneck right now in the rollups in general, and especially in the and the zk rollups too, not an exception, is the data availability. So here we're also working a lot in the EIP 4844 to integrate that when it's available. This will give 10x, at least in capacity in Ethereum. And we'll see if this is equivalent to 10x in cost too. And we're also working in the compression so that the data, we expect to have a compression rate of 6-7x. That's going to be on top of this 10x. So we expect that in the upcoming month, we probably will have an increase of the throughput or reduction of the price, if you want, more or less, of about 50, 60, 70x in the upcoming year. So that's an important improvement that we will see in the upcoming month. Okay, but let me explain. That's what I wanted to explain, especially in this talk. It's about I want to talk about the new proving system that we are working on. Okay, so if we see the current prover, which is quite efficient, it's a monolithic proof. It's a proof that it can more or less prove 10 million gas block, I mean 3 million gas of execution, and it takes about 1.5 minutes, 2 minutes, depending on in a huge server, in a server in 128 cores with 0.5 terabyte of memory. It's a huge server, but it takes about this 1.5 minutes. Okay, but the problem of this proof, one of the problems that is that it's a monolithic structure. Okay, and we have the number of operations that we can put in this proof is limited. For example, the number of arithmetic operations is limited. The number of catch-checks is limited. Even the number of executions, so the complexity of the transactions is limited. I mean, it's a bone there. So system is an L2 mainly. So just to be, this is not really exactly the same as Ethereum. I mean, normal users should not see a problem if they are not doing strange things. But if you, for example, do a loop of catch-checks or a loop of just arithmetic operations and you extend these places, then this transaction will be executed but will be considered like a no-operation transaction. So that's why we are always able to prove everything. But maybe there are some transactions, very strict transactions that goes out of these counters. And this is a little bit of difference between what's Ethereum 1, what's Ethereum, and what's a layer 2 rollup. So in order to solve that, we are changing a little bit the architecture of the proof, and instead of having a single proof, a monolithic proof, the idea is here we are using a lot of recursion. So we are taking advantage of recursion to so instead of having a single proof, we have like different subproofs, maybe one proof of binary, one proof of arithmetic, one proof of main on the main state machine, and then we aggregate all this proof in a single proof. Actually, it's not really independent proof. We call it parallel proof because these proofs are generated at the same time. Okay, but we have like a one level of recursion where we can aggregate. And the cool thing of this is that, for example, we can, I mean, if we are using a lot of arithmetic operations, we can put a big proof with big arithmetic, or if you are using not many arithmetic operations, we can have a smaller proof, a proof that can be computed much faster. Okay, so we optimize much better the resources that we have in the monolithic. In the monolithic proof, sometimes, I mean, if the transactions don't use many ketchups, there is a big part of the proof that we are paying anyway that's maybe unused. Okay, so with this system, we can optimize much better the resources that we are using. And not only that, we can also do, for example, if we have a lot of binary operations, one thing that we can do is we can generate as many binary subproofs and then aggregate them all together, and in this subproof aggregate them together. So this allows us, this structure allows us to do as many operations, as many operations that we need in order to solve in order to execute, in order to prove any transaction, no matter how complex or how difficult it is. Okay, and this has a lot of advantages regarding this. Okay, so this is the advantages of the proof. But in order to do that, here is when we see this structure. The problem here is that because there are different machines, that there are different subproofs, and they even have different sizes. The idea is how we connect one each other. In a monolithic proof, it's relatively easy because we do a normal lookup, structure that with the two polynomials of the same degree. But with these bad cubes, I mean, we have, and what I want to explain now is a little bit what's this technique, because this is very powerful, and this can be used for doing this huge proof on proof that can prove you can prove as whatever you want. I mean, you can extend this proof with the resources that you need to compute any proof. Okay? So first of all, I'm going to start now a little bit the technical discussion on how we are doing that. First of all, I want to do a little bit remaining of what a polynomial commitment is. All these proofs are based on polynomial commitments. The idea is that we are setting up a set of polynomials. Polynomials, for people who don't know, is a polynomial is a normal polynomial. Instead of working with normal real numbers, we are working with finite field numbers, but they follow exactly the same polynomials. And the idea here is when we are saying a polynomial, mainly you can understand this as an array of points. For example, if we do a line is defined with two evaluations, so it's 2 points. So if you do a degree of polynomial of degree 1000, that means that it's defined with 1000 points. So it's the same as saying that committing to an array of values. Okay, so the idea is that we commit to a set of polynomials. Okay. The verifier sends just a random number, and then we just do an opening. So we prove that those polynomials that we committed, when you open a certain point, is given a value. Okay, and then the verifier can check the polynomial equations, but they check just in a single point. And if this number is, and the field is big enough, and this number is big enough, then you can be sure that these polynomials are so that these polynomials are okay, and that follows these constraints, these identities. Okay, these polynomials. The cool thing of these polynomials is that you can have relationship between one row and the next row. So these relationships of polynomials, mainly what they do is the state transitions. So you can do a state transitions. So you can generate polynomials. These polynomials can be state transitions. If you have a state transitions, you have processors. If you have processors, you can execute programs. If you can execute programs, you can prove whatever you want. Okay, there's a little bit the full stack of a prover altogether. So that's a little bit the important part. Okay, so here, for example, you see a polynomial. That the next step, so the next value of a polynomial should be, for example, the previous value. Okay, well, this is a mistake here. Okay, so how we do. One of the things here is that when we have two polynomials, one of the important part is because we want to connect like two state machines. We want to do a permutation check. Okay? So permutation check, what means? So I have two polynomials, and I want to check, imagine the polynomial f and the polynomial t, and I want to prove that the polynomial f is, the evaluations in the polynomial f are exactly the same that the evaluations in the polynomial t, but with a different permutation. I mean, it's a different order. But I want to prove that it can be any order, but are actually the same numbers. W's, this is where you evaluate the polynomial. It can be any number. In general, we are taking what is called root of unit, but these are different numbers, just random. I mean, it's kind of they are not random, but they are specific numbers in there. So this is the evaluations. This polynomial can be identified with these evaluations. T polynomials can be identified with this evaluation. And then the question is how we can prove that these polynomials, one is a permutation to the other. Okay, so the main here the main, so how would it work? Well, it's 2 steps. So it's actually two steps prover. So in the first we commit to the f and t polynomials, the ones that we want to check the permutation. The verifier sends beta. Here you see that's an interactive protocol. Okay, all these interactive protocols, they can be converted to a non-interactive. It's a Fiat-Shamir method, and the idea is that this beta can be just the hash of what's sent before. Okay, and then because the hash is reversible, then you cannot detect beta. So you can convert everything to a normal proof, a non-interactive proof. But it's a good way to see it this way, okay? So we commit to the polynomials, we get this random beta. Here the prover generates a new polynomial. It's a polynomial, a z polynomial. It commits to the z polynomial. And then the idea is we do the same. Once we have these 3 polynomials committed, then we do a normal opening, so the same that we did before. The verifier sends a random number. Here we open all these polynomials at the different places, and then we check some equations. Okay? So going back, actually, what's this z polynomial? Well, this z polynomial mainly is what we say is the grand product. Okay? So the idea is what we do is in the first one we put. You see here is 3 is the f. So you see the f. We do add f plus beta, and this in the numerator, and in the denominator we put the t plus beta. Okay. In the next step, actually we accumulate. We do a grand product. We take the previous one and we multiply in the numerator the f, and in the denominator the t, but with added beta. Okay. So you see. Once we do all the steps, you see that the 3 plus beta, 2 plus beta, 4 plus beta, 1 plus beta, all of them are gonna pair. You see here in the last row, here all of them are gonna pair in the numerator. Okay, but because I'm adding also the t, these are gonna pair in the denominator. But if it's a permutation, everything that's numerator should be the denominator. Maybe in different order, but everything should be in the numerator. So the result must be this to 1. Okay, so how I express that in polynomial equations? Well, in the first equation here, it just says that the last line must be 1. L4 is another polynomial that's 0 everywhere except the last line. So L4, if in the first 3 columns is 0, so 0 times whatever is 0, it's going to follow whatever it happens. But when L4 is 1, this is in the last line, then Z must be 1. So in order for this to be 0, Z must be 1. Okay, so I'm forcing that this is 1. Okay. And in the next one here, what I'm saying is Z prime is the next row. So the next value must be the current value times, well, the next value plus beta, the next value plus Z. Okay, so this is just the 2 equations that I'm checking. Okay, so as we saw before, the full protocol is just do the commit, send this beta random, I commit to Z, and then I just do the openings. Which openings I do? Well, I just need f prime, FWR is f prime, it's evaluation in one point. So in the next step, T prime, Z prime, and Z. So we have these openings. I'm saying the opening is this, in this point is this. I prove, so this openings goes with a proof, so I'm sure that these openings are this. And if these evaluations matches these equations, that means that all the questions matches the polynomial. And if this happens, means that these polynomials, the only way for this to happen is that these polynomials, one is a permutation on the other. Okay, so this is the basic permutation check. That is very much how it works. Okay. Here there is a newty, and it's something is like here what we are doing. You see the trick here is that in the numerator we are adding the f, so we are adding the two polynomials. In the numerator we're adding one polynomial, in the denominator we are subtracting one polynomial. Well, there is a way that instead of multiplying in the numerator and the denominator, I can do is, well, instead of multiplying, I'm just adding. So I'm adding, instead of, this would be, I'm adding the f in the numerator and subtracting then the t polynomial. Okay, so you see here. Okay, but the difference here, of course, I cannot put it in the. I need to do this inverse for the protocol to work. But the cool thing here is that no, this way is additive. It's not a grand product. It would be more a grand sum. Okay, so I can do these things for adding. The idea is exactly the same. The thing is that, of course, the last number is not going to be 1. It's going to be 0, because at the end, everything needs to add up, sum up to 0. So these equations are also changed. But the idea is exactly the same. This is what we call a lookup. Okay, and this is kind of a new thing. Okay, what for these permutations, if we sophisticate a little bit, we are doing a permutation. Until now, we do a permutation of two polynomials, but we can do also the same with various polynomials. If I have three polynomials, instead of having f, I have f1, f2, f3, and I have t1, t2, t3. I just can I can do exactly, so the idea is to do the same, but instead of putting f prime, I can just do a random linear combination. Alpha, this is a challenge number set instead of like beta. I mean, this is like another challenge sent by the verifier, and I can add I can do a linear combination here of f, and the protocol works exactly the same. So I'm adding this part, this f, I want this f needs to be permutation check of t. Okay, so I can do this adding. This is a linear equation, so I can prove exactly the same way that we did before. Okay. This is yeah, another important, interesting thing. Right now we have checked what we did until now is a permutation check. Okay, so we are checking that one polynomial is exactly the same as the other. But sometimes what I want to do is check that it's an inclusion, so that whatever is in here, for example, here is 3, 2, 2, 1, it's included in 1, 2, 3, 4. Okay, so this, for example, would be a kind of a range check somehow. Okay, so 3, 2, 2, 1 is, so 2 is 2 times, but I want this to also happen. Okay, so one thing that I can do is I can add this extra column here, we call it C, and that says how many times this value appears there. So if I say this is 1, this is 2, this is 1, I can put this, I can just change the questions. Instead of adding this one time, I'm adding C times. Okay, so that's the same as multiplying by C times. And this is the same. So here I just converted one thing that's a normal permutation check to a normal lookup. So this, the fact that this adding, this allows us to do these lookups very, very easily. If we do it in the multiplication, this C instead of being a multiplication would be an exponent, and then exponent in the polynomials, this is much more difficult to prove. But because we have this structure that we can do this with adding, with this grand sum way, then doing permutation, doing lookups, then it's much easier. Okay, so we have this structure. We are in here, and here we are adding n times, C times the thing here. So we have the with this we solve what we call the lookups. Okay, between two polynomials. Okay. Okay, what happened when I have right now f and t are in the same proof, and then this is relatively easy because I can do these polynomial checks. So I can do these polynomial identities when the polynomials are the same degree, are in the same proof. Okay, but what happened when I have, for example, the f's is in one subproof and the t's are in another subproof? Maybe with different degree. I mean, maybe this is degree 4, this is degree 8. Okay, so what I can do here is, okay, I have a state machine. Here I can have a state machine that's doing exactly the same, but just adding up. So I'm just adding the f prime polynomial. So at the end, it's not going to be 0. This is going to give some number, okay? And in the other side, I just can do the same, but I'm just subtracting. So when I'm subtracting this sum here. So I have one output here, one output here. So I have subproofs, 2 subproofs that have one output and one output. So if this output, I can put it as a public input as a public output of these subproofs, then what I can do is in the bigger proof, I can check that this number is exactly the same, or if you want that these numbers sum up 0. Okay. So the idea of this sum is that I can have this, call it this column. I mean, I can compute this sum in one side. I can compute the other sum, the subtraction in the other side, and then in the proof that aggregates the 2 proofs, I can check that this public output is exactly the same. So this allows us to do permutation checks or lookups between different subproofs. Okay, but this is even more powerful. Okay, so imagine that I have different subproofs. Okay, what I can do is I can have this in each of the subproof. I can have this Z column. We can call it the bus column. And it's a bus where each subproof is adding or subtracting things. I mean, for example, if in the main machine I'm assuming that one multiplication is valid, I'm assuming that in the same machine, I'm adding that to the bus. And in the arithmetic state machine that I'm proving, so something that in the main state machine was assuming, but needs to be proved somewhere, where in the arithmetic state machine, they can prove that this arithmetic is valid. So they do the actual multiplication, they prove that's valid, and what they do is they subtract that in the bus. Okay, and this can be in a different proof itself. Okay, so and I can also add. I mean, any function. I mean, the binary operation. Maybe it's a different thing that I'm adding to the bus. Ketchup, I'm adding that to the bus. Okay, or even a range check. So whatever I'm doing, I can add to the bus or subtract it to the bus when I provide or when I require. Okay, and I just need one column where I add all these things. Okay, and at the end, I'm just taking all the buses and I'm just checking that the addition is 0. Okay, so. Yeah, this is the idea. Okay, for example, this is in the main state machine. I can have here would be, for example, the arithmetic state machine. I'm assuming that A times B is C, so I'm adding here A, B, and C. This is a 1. This 1 is the operation. 1 means the operation arithmetic, for example, and 2 means the operation store. Okay, so I'm adding to the bus an arithmetic operation, so 1 plus 1 alpha, so this is a selector of what I'm adding to the bus, because it's alpha, it's going to be random somehow. Here, you see that they can have even different size of parameters, okay? I'm adding this because I'm assuming, and then, for example, in the arithmetic state machine, I'm subtracting because here I'm proving that A times B is C, and in the store state machine, I'm just proving that the store of A and B is correct. Okay, but you can extend that. I mean, the full proof has like a lot of assumptions, and you're adding a lot of things to the bus, subtracting a lot of things to the bus. You can add a lot of things to the bus at the same time, because at the end you are adding, and this is very powerful. Okay. Another thing is that you can do is assuming these things to the bus. Of course, you can have different state machines adding and subtracting things to the bus, but you can also have what we call it public tables. Also, the verifier. Because the verifier, they need to compute the transcript somehow. So they have alpha and beta. So they can also add, for example, include some transactions. For example, the verifier can write things in memory. Okay, and if I write is an instruction, they can compute the addition of all the bytes. So they compute a value, and then this can be like an input to the circuit, and this input is added to the sums of all the buses, and this is what needs to be 0. So you can delegate part of these operations to the verifier. Okay, so this is, for example, it's a way to save a lot of public inputs. In general, what we do is we hash it and we hash it inside, but with this technique, the idea is the verifier can just do this linear combination, I mean, these multiplications, I mean, these additions, these special additions, and then just pass it as a public input and check inside the verifier that's in here. Okay, so this is another trick. So with these techniques, you see that first we are saving a lot. We are saving a lot of polynomials in the proof. So we expect a huge improvement just because we are reducing like about 1/3 of the polynomials. Okay, so this is going to be a good improvement. But the most important part, well, the most important part here is that we expect a lot of saves because we don't need to have state machines of exactly the same size. We can grow that. We can have this dynamic size that we can grow, and so we are just paying the prover what we are really using. And it's another advantage is that the design of these state machines, they don't need to be constrained by these size. Okay? You can do, for example, state machines that are very wide. I mean, for example, you can do a ketchup in one line, okay, but with a lot of polynomials, very horizontal. Okay? Or you can do ketchup with very few polynomials, but lots of rows. Okay, so right now we are a little bit constrained because at the end we want to. At the end, what we have is a fixed number. But with this system, with a variable degree, you can do whatever you want, and you have this flexibility. So this will allow also to redesign some of the pieces in a that's going to be much more optimal itself. So all this winning, we expect that we haven't seen the numbers. We need to check, but at least a 3x in the improvements of the prover for sure are going to come. Okay. For this new concept, the idea we are expanding PIL to PIL 2, and we are PIL 2 will have a lot of new things. The most important thing is that we'll support these bad cops, so we will be able to design this, we call it hardware. I mean, it's these polynomials, but it's this low layer, this arithmetization with PIL 2. There is a lot of new, a lot of new things that are added in PIL 2, like, it's more functional library. It's a lot of, for example, of the constants that right now are site scripts, they're going to be embedded inside the PIL 2, so it's going to be even easier to audit and to verify. You will be able also to access different rows. I mean, there is a lot of new. You will define. Right now, the PIL 1 is very. The constraints that so what you can do permutation checks. You can do lookups. The things that you can do are very specific. With PIL 2, the idea is that you can extend. I mean, you can add new protocols and all these. These permutation checks. They are programmed in PIL 2 itself. So these are more flexible and more. The language is easier, but it's more flexible. I mean, you can write PIL 1 in PIL 2 somehow. Okay, so this is going to be very flexible, and at the end, the idea is to be able to build a kind of a library of these components. We call it hardware components, but actually it's not hardware. It's polynomial. These are proofs. These are polynomial identities somehow. Okay, so the idea is that we can have a library of Ketchup, arithmetic, maybe a Patricia try or SMTs, whatever libraries that are very specific. Okay, you can have processors. Processors here can be zk specific processors, or can be, for example, a RISC-V or some of the things of these processors. And the idea is that at the end you will be able to run a code. Ideally, you can have, for example, a code written in Rust or in Golang, and then you can compile for these processors. If you just have a processor, this is not going to be optimal. But if you have some of the pieces, like arithmetic state machine, the ketchups, that or some specific things that the program will need, maybe in the program side they will be as a normal software library, but then they will end up using this like a specific hardware and this specific piece that they can plug all together. So we will be able to generate proofs faster, and maybe not using a special assembly, maybe using even high-level language. Okay, so this is the main goal of this PIL 2 and what we are building as PIL 2. And yeah, that's very much it. Just for you, the people that don't know about the zkEVM, just ask them to try it. On Saturday, I think we have a Polygon Connect somewhere. I'm going to be there. If anybody will have doubts or want to talk about the Polygon, what we're doing in the Polygon zkEVM, I'm fully available here on Saturday. So that's my presentation. Thank you. Not sure if there is questions.
Molt bé. Does anyone have any question that they would like to ask? I'm sure you all have a math question or a lot of numbers.
It can be, they can be no technical if you want.
No, oh, here, sorry.
Thank you for the presentation. Definitely not a math-related question, but just curious from your perspective, these optimizations, what kind of new possibilities does it unlock in terms of like new business models or more like decentralization, or is it part of like a bigger roadmap that would allow for new innovation on top of Polygon?
Yeah, so these optimizations, I mean, they will, first of all, they will allow to do what we call it type 1 rollups. That means that rollups that are closer to Ethereum. Okay, so without, I mean, we will be able to prove exactly the same block that happened in Ethereum. Okay, so we are getting much closer to that. Okay, this flexibility of having a proof that's variable size. I mean, that you can prove whatever you want by extending. Okay, this is one thing that's important. The second is optimization. I mean, building these proofs, it requires a lot of hardware computation. Okay, with this we are getting better. I mean, the idea is to get closer to prove things. Okay, the other thing that I mentioned a little bit here below is like the holy grail somehow would be that you just take a client, an Ethereum client. I mean, you take Erigon or you take Reth or Geth, and you don't need to audit that. The idea is that you can take that code and then compile that, but compile for the zk processor. So you will be able to prove whatever you want just by recompiling the final thing. Okay. Right now, this is not possible because it's very ineffective. But when you build this, when you put these specific components that do some specific parts very efficiently, then you remove that from the main processor, and then this is what will make it possible. From the decentralization perspective, I mean, this is a different topic. But what's important here is in the forced transactions. When the forced transactions, the important part of the forced transactions is that in order to roll up, if you have a centralized sequencer, this centralized sequencer can censor you. I mean, they can say, okay, this transaction, I don't like it, so I'm not going to include that transaction. So, and then if you don't do anything else, then your funds could be stuck inside the roll up. Okay, so there is a mechanism that's called forced transactions. The idea is, if I'm locking you, I mean, if I'm not forcing transaction, if I'm not sending your transaction because I'm censoring you, you can take this L2 transaction and send it to L1. Okay, and then in the sequencer, I'm forced to include that transaction. Actually, you will be able, the way is not that I'm forced, you will be able at some point to take that transaction. If I don't include it, you will be able to include and to sequence that transaction in the chain. So these transactions, you have the warranty that this transaction is going to happen, whatever happens. So there is no way for censorship resistant. It's not really true because it's a censorship resistant in the sense that I cannot lock you, but effectively, I can kick you out of the network, okay? Because I'm not censoring you. Probably what you will do is an exit. That's why it's important decentralized sequencers, okay? But just the thing is because we want to build systems that are universal, okay? That anybody can use it here. The centralized sequencer can decide somehow who can use the system or not, okay? So that's why it's not perfect. Centralized sequencers are not perfect, but it's probably the word centralized sequencer is not the best word. I mean, it's very good. I mean, centralized sequencer means it's a system with censorship resistance that works well, that the sequencer cannot do anything but decide who can be in the network. They can kick you out in the network. Okay. Well, I mean, there's a lot of things, but this is it's different topics. But this is the main work is for working in that direction. Okay.
Okay. So unfortunately, we don't have more time for questions, but I'm sure you can ask him outside, and more than happy to answer the questions. So big applause for Jordi.